Hey guys, and welcome back to another video in chemistry. So today we're talking about theoretical yield versus actual yield. So what we're talking about with yield is how much product we've actually created. So in any reaction, you never get the exact amount of product that we predict. Just doesn't happen. Nothing works perfectly. There's always going to be a little bit of unreacted stuff left after our reaction. And so the stuff that we do get, we call our actual yield, the amount of product that is actually produced. Much better. Theoretical yield is the amount of product that we predict would be made using stoichiometry. And this is if the reaction was perfect. So if every last atom reacted in exactly the way we expected it to, and every single bit of product or reactant that we could turned exactly into product and nothing else. So if the reaction was absolutely perfect, what theoretically should have been the amount of product that we created? And then we can figure out how efficient was our reaction. What was the percent yield? So, in the perfect world, you'd have 100% yield. That means every last bit of chemical that we started with turned into product. So to find your percent yield, you take the mass of your actual yield, so what you actually got, divided by the mass of the theoretical yield, what was possible. In like a test score, you might get like 9 out of 10, right? You got actually 9 marks out of a theoretical perfect test of 10. Right? There was 10 possible marks in theory. You could have got them all, but you only got 9, so you get 9 out of 10, 0.9, or 90%. You can do the same thing with chemistry. Now, if our percent yield is only 50%, well, that means you made 50% of the product you were predicting should be made. A bunch of your reactants didn't turn into products. And that would be a problem. You got to figure out where that other 50% went. Are they still sitting in the beaker, just not doing anything? Why aren't they doing anything? Did they turn into something else maybe? Did they react with something you didn't expect? Like maybe they reacted with the air and something happened. So percent yield tells you kind of how effective your reaction is. So for example, what is the percent yield for a reaction if you predicted the formation of 21.0 grams of C6H12 and you did the reaction, you recovered 3.8 grams of C6H12. So plug it in the formula. Percent yield is actual over theoretical. So our actual yield was 3.8 grams divided by our theoretical yield. Theoretically, we could have got 21 grams, apparently. You divide those, gives you 0.18. So you have an 18% yield. Oh, that reaction did not go very far, did it? So we got another reaction here. S6, which is a solid, reacts with 6 oxygen gases to form 6 sulfur dioxides. All right. Now we started with 384 grams of S6. So we've got 384 grams right here. How many grams of SO2 should I get? Now, SO2, well, I guess not SO2, but grams, really not that handy for us, right? We can't use grams. This is a stoichiometry problem. I need to go to moles. So, okay, S6. If I have to go to moles, I'm going to need the molar mass. So I find sulfur on my periodic table, and it turns out that sulfur has a molar mass of 32.065. And S6 is made of 6 of those, so I just times it by 6. So my molar mass then, 192.39 grams. So I have 384 grams of S6. I want to change out of grams and into moles. And I know 1 mole is 192.39 grams. So let's do it. 384 times 1 divided by 192.39. So it turns out I've got 1.9959 for ease of fitting it into the notes, I'm going to call it 2 moles. I have 2 moles of S6. All right. But I need to get to SO2. Guys, remember that formula? What do I have divided by, well, I'm just going to call it my recipe. How much I have divided by what I could get. So I have 2 S6s. And in my recipe, my mole ratio, it's 1 S6. And in my recipe here, 6 SO2s. And I need to figure out how many SO2s I'm actually going to get. So 6 times 2 is 12. 12 divided by 1, I'm getting 12 moles of SO2. Holy smokes. But in order to find theoretical yield, I don't need moles, I need grams. So I need to find the molar mass of sulfur dioxide. Sulfur is 32.065. Plus, I've got 2 oxygens. Let's call it 32. I need to change out of moles into grams. 1 mole, and I just did this molar mass calculation on my calculator really quick, but I'll jot it down here. It's 64.065. All right, I'm going to add a new page here. So, 768.78. That's the answer to that question. That is my grams theoretical of SO2. Let's go back. What did I have? I started with 384 grams, assuming an unlimited supply of oxygen. Theoretically, I should be able to get 768.78 grams. That's my theoretical yield. 768.78 grams. Let's circle that so I can find it later. Now, I did the reaction, and I made 680 grams of sulfur dioxide. So, percent yield is what I actually got over my theoretical. So actually, I got 680 grams. In theory, I should be able to produce 768 grams. Grab the handy dandy calculator again. 680 divided by 768.78. 0.8845. So I have an 88.45% yield. That's quite good. Of a possible 768, I got 680 out. That's not bad at all. Got lots of it. So most of my reaction actually completed really well. Oh, that's just that slide again. And now that leads us into a concept called limiting reagents or limiting reactants. So let's say we're building a Lego house. You have an instruction manual that tells you how to build this beautiful Lego house. You need 10 white blocks, you need 10 black blocks, you need 1 door block, and you're gonna need 4 windows. Cool. So I dump on the table a big old bucket of Lego. You got 52 white blocks. You got 64 black blocks. You got 7 doors. You got 50 windows. Go, build me some houses. So I want you to take a minute here, maybe pause the video and tell me, how many houses can you build? All right, so hopefully you pause it there and try to figure it out a little bit. Basically, I'd say, okay, if it takes 10 white blocks per house, and I have 52 white blocks, that would give me 5 houses worth of blocks, right? This one, I have 6 houses worth of black blocks. I've got 7 houses worth of doors, and 4, that gives me like 10, that gives me like 12 plus houses, more than 12 houses worth of windows. All right, so how many houses can I build? Can I build all 12? Well, no. I'm going to run out of white blocks first, right? I could only build 5 houses. After my 5th house, I have used up 50 white blocks, right? After 5 houses, I only have 2 white blocks left. So I've used up 50 of them in those 5 houses because each one required 10. So I have 2 white blocks left. I'd have enough of everything else to build more houses, but I'm out of white blocks. I'm done. I cannot make a house that matches the instructions. So why can't we build more? I've run out of one of my Lego blocks. When we build Lego structures, we can only build a certain amount because you got pieces left over, but not enough for a full structure. We call those pieces like a limiting factor, right? Without having more of them, you couldn't keep building. Doesn't matter if I have 1 billion doors. Without more white pieces, I'm stuck. I cannot make more Lego houses. And in chemical reaction, there are also limiting factors, but we call them limiting reactants, or sometimes you hear them called limiting reagents. Same idea. A limiting reactant is the chemical, the reactant, that keeps the reaction from proceeding, keeps it from going on, because it runs out. All other reactants would be in excess. So up until now, we've said like, hey, here's magnesium plus oxygen gas. We're going to form some MgO. Okay, let's pretend you have 1 gram of magnesium and excess oxygen. We've forced you into, this is your limiting reagent. You're going to run out of magnesium because you've got as much oxygen as you need. Now we want to say, okay, what happens if you have 1 gram of magnesium and 1 gram of oxygen? Which one is going to run out first? Which one of these is going to limit your reaction? Which one's going to slow you down? So that's where we're going. That's what we got to figure out. Which one is excess and which one is limiting us from continuing? So 2 moles of magnesium reacts with oxygen gas. I should put that's a solid. That's a gas. That's a solid. That gives you 2 magnesium oxides, right? That's the burning magnesium reaction we did in the lab. 4 moles of magnesium. So I give you 4 moles of magnesium. I'm not going to make you do grams into moles again. You can do stoic by now, right? Theoretically, I'm going to give you 4 moles of magnesium. I'm going to give you 3 moles of oxygen. What do you run out of first? So the trick is, calculate the number of moles produced twice. I want to find out how much product I can make twice, once for each reactant. So let's say, if you remember how much I'm for, we're going to use the stoichiometry equation. What you have over what you need, right? Over what's in the recipe. So I have 4 moles of magnesium. Let's just do the magnesium like this. I have 4 magnesiums. I need 2 in my recipe. I don't know how much product I'm going to make, but I do know that 2 are in the recipe. All right. 2 times 4 is 8. 8 divided by 2 is 4. So I would make 4 moles of magnesium oxide. All right, so that's my first calculation. If I used magnesium, I could make 4 moles of product. Now let's check oxygen. So I have to do this calculation twice. So oxygen, I was given 3 moles of oxygen, and my recipe requires 1. I don't know how much product I need, but my recipe spits out 2. 2 times 3 is 6. 6 divided by 1 is 6. X equals 6 moles of magnesium oxide. Okay. So if I use the magnesium, I can make 4 moles of product. If I use the oxygen, I can make 6 moles of product. So which one's going to run out first? The one that can only make 4 moles of product. So you check it twice, or if you had 3 reactants, you could check it 3 times. You find whichever one is the smallest. Whichever one is the smallest, you're going to run out of first. Because I could only make 4 moles of magnesium oxide, I will never get to 6. I will never run out of oxygen. I'm going to have extra oxygen. So magnesium's limiting. There's only enough to create 4 moles of product, not the 6 that oxygen could. Another way to think about it is if I have 4 moles, I can do this reaction twice, right? If I need 2 per recipe and I have 4 of them, I can do my reaction twice. But if I have 3 oxygens and I only require... let's go back there. If I have 3 oxygens and I only require 1, I could theoretically do 3 oxygen reactions. So magnesium's limiting, there's only enough for 2 reactions, where I have enough for 3 oxygen sets. Again, think of the Lego blocks. I'm going to run out of white blocks, magnesium, before I run out of black blocks, oxygen. There's just not enough to make it happen. So mathematically, if you just want a way that always works, you do this. You check how much product you would make using one, check how much product you'd make using the other, and see which one makes less product. Whatever makes the least product is your limiting reagent. Now, how many moles of oxygen are left? So we said we're going to run out of oxygen, or run out of magnesium, but we have extra oxygen. How much? Well, first we got to find out how many moles of oxygen would be used up if we used all the magnesium. So this is stoichiometry again. If I gave you 4 moles of magnesium, ignore that. How much oxygen should I use? So if I use all 4, I've been given 4, and of course magnesium needs 2, right? If you look at that formula there in the recipe, magnesium needs 2. How much oxygen will be used up? And the recipe gives me 1. 1 times 4 is 4. 4 divided by 2, just cross multiplying and dividing here. X equals 2. I would use up 2 moles of oxygen gas. All right, so how many moles of oxygen are left over? Well, I'd use up 2 of them, and I was given 3. So, all right, I've got 3 moles given minus the 2 moles I used up. 3 minus 2, I would have 1 mole of oxygen left. So, quick recap. To find your limiting reagent, you use stoichiometry to calculate, all right, if I was just given 4 moles of magnesium, how much product would I make? Then you do it one more time. If I was just given 3 moles of oxygen, how much product would I make? You find whichever one's bigger, that's your limiting reaction. If you want to find the excess, you take your limiting reactant and pretend that's the only one you've got. If I only have 4 moles of magnesium, how much oxygen would I use up? Then you can subtract what you were given from what you used. I want to jot that down as maybe a set of steps. If you're having trouble following all this, I want to rewind a little bit and jot down those steps in order. But I'm going to step through it one more time here. With the complicated one, we got decimals all over the place. Ooh, scary. 17.75 moles of aluminum react with 13.86 moles of oxygen. What's limiting? What's left over? So I got to start by figuring out what's limiting. So let's start with aluminum. I'm given 17.75 moles. I need 4 moles in the recipe. It spits out 2 moles of product. How much am I going to be left with? 2 times 17.7, oh, I did decimal there, 17.75. Divide that by 4. That's not right. 2 times 17.75 divided by 4. Yeah, that looks better. I have 8.875 moles of aluminum sulfate. All right. Let's check oxygen. I'm given 13.86 moles of oxygen. My recipe requires 3. Let's look at my product again. I want to see what I can make. I'm given 2. I need to find that. 2 times 13.86 divided by 3. So with oxygen, I can make 9.24 moles of aluminum sulfate. So which one runs out first? If I start these happening at the same time, what do I run out of first? Well, aluminum, because I can only make 8.875. So we know aluminum is limiting. There's question 1 answered. Question 2, how many are left over? So to figure out how many are left over, I pretend that this is all they gave me. So I have 17.75 aluminums. That should be moles of aluminum. And my recipe uses up 4 at a time. So if I have that, how much oxygen will I use up? Well, I know I use 3 at a time in my recipe. So how many moles of O2 get used? Or how many moles of O2 will I need? 3 times 17.75 divided by 4. Let's call it X instead of question mark, just because it's easier to write. I will use up 13.3125 moles of oxygen. That's what I'm using up. If I give you 13.86 and I use up 13.3125, what's left? 13.86 minus that, 0.5475 moles of O2 gas will be left over when I'm done. So just over half a mole left over. So again, quick recap to follow that through. I check how much product I would make twice. Once for aluminum, once for oxygen. And I find which one's smaller. In this case, aluminum was smaller. That means I should run out of aluminum first. All right. So if I run out of aluminum first, then that's the one I have to check to see how much oxygen I'm going to use, because it's going to run out first. I can't use the oxygen because I have too much of it. So I plug in how much aluminum they gave me and pretend that I don't know how much oxygen I have, because I don't want to know how much I have. I want to know how much I'm actually going to use once the aluminum's been used up. So I calculate that out, and I'm going to use up 13.31 moles of oxygen, and I can check back into the question and see what they actually gave me. Now, this number should be bigger every single time. If this number is not bigger, you may have screwed up your limiting reagent calculation. Because that number's smaller, that means you should run out of oxygen first, right? So just a little troubleshooting thing. If that ever turns out that for some reason you do the subtraction, you end up negative, you might have picked the wrong limiting reagent. But that pretty much wraps up our limiting reagent stuff. Hopefully that is making sense. I'll give you lots of time to practice with that, because it's a very important concept to wrap your head around. But if you have any questions, you know where to find me. And other than that, have a good night, guys.